In squares, it'll come out to be a 45, 45, 90 triangle. And then in everything else, there are all kinds of different right triangles. You're going to be using trig for everything else. But this is the generic process. You first need to find the measure of the central angle. Then you introduce that apothem, and it bisects that angle, bisects the side length. Bless you. Solve the right triangle to figure out everything that you need, and then plug it into that formula. Okay. So, on the first page of homework, page 220, they get you used to finding those measurements of those central angles. They get you in the habit of finding the measures of those central angles. So for 1 through 4, I know you weren't assigned all of them, but for 1 through 4, you just take 360 degrees, divide by however many sides there are, and that's the measure of your central angle created by 2 consecutive radii. That's the first step we got to do. This question's like 1 through 4. Then from there, questions 5 through 10, they use this dodecagon, which has how many sides? 12. Dodecagon has 12 sides. And then if you look through those questions, they ask you to solve for all kinds of different central angles created by consecutive radii and also non-consecutive radii. We're really not going to focus on that. We're going to, I understand why they did it, because you need to understand what's happening within these regular polygons. But our main focus is going to be 2 consecutive radii. You're going to find the measure of that central angle. So what is the measure of the central angle for this dodecagon? Say it louder. 30 degrees. 360 divided by 12 is 30. So that's this angle right here in black ink. Then from there, you're going to introduce your apothem. That's going to do 2 things. It's going to bisect the whole side length. It's going to bisect one side length. And it's also going to bisect that central angle. Because we already know what that central angle is, we can quickly find out what half of it is, which would be 15 degrees. Once you do that, you're then going to turn your attention to that right triangle that is being formed by a radius, apothem, and half of the side length. We know that this angle up top is half of the central angle. In this case, with the dodecagon, it's 15. You're going to use trigonometry to solve for the apothem, half the side length, or the radius. Just depends on what you are good at and what you are searching for. Number 12. Different story. Number 12 is a different story. Because as these questions progress through this, on this page 220, it's getting closer and closer and closer to finding the area of these regular polygons. So up at top, we were just finding the measure of that central angle. Then in the middle, we were finding measures of other angles and just kind of getting a good feel for how these regular polygons are going to work with these radii, with these apothems, and so on and so forth. But then now, in number 12, we're actually solving for one of these lengths. What shape do they give us? Hexagon. Okay. So what is the measure of the central angle created by 2 consecutive radii? So this is the central angle. It's going to open up to one side length. We can find that by taking 360 degrees divided by however many they are, which is 6 sides. So this is 360 divided by 6. 60 degrees. Then we're going to introduce that apothem, which is the altitude of this isosceles triangle. It's going to do 2 things. It's going to bisect that opposite side, which is one side of this regular hexagon, and it's also going to bisect that vertex angle up top. After you do that, you're going to then turn your attention to this right triangle that's created by these 3 special segments. One leg is going to be the apothem. The other leg is going to be half of the side length of this regular polygon, and the hypotenuse is always going to be the radius. We're always going to be able to determine one angle measurement in this right triangle. This is the one that's being formed by the apothem and the radius. We can find that because we know that that central angle is being bisected by that apothem. So in this case, what's the measure of that angle? 30 degrees. Which makes this right triangle a what type of triangle? 30, 60, 90 triangle. What do they give us about this shape? Gives us its diameter. I don't see diameter anywhere here. So what are we going to do with that?
Divide it by 2 to make it a radius.
We got the radius. We can divide it by 2. So what is the radius of this shape? 11. So I'm going to erase R and put 11 for that radius. And then we're going to solve this right triangle. 30, 60, 90. These are the three interior angles of this right triangle. Below them we're going to put the extended ratio that the side lengths always follow. L square roots of 3, and 2L. Remember, I use that variable L that stands for the short leg. If you look at your formula chart, it uses X. I don't like that because it gets confusing. Because in some diagrams, X is representing the long leg. And so if you get confused, you're like, wait, my X or this X? Or this formula is X. What is X? It just gets out of hand. So we just use L. They give us the hypotenuse is 11, so I plug that in. That's my formula. 2L is 11. So how am I going to solve for the short leg? Divided by 2. I prefer improper fractions, 11 halves. However, 5.5 is also an acceptable answer because that's a terminating decimal. So I'm okay with that. 5.5. Now how am I going to find the long leg? Square roots of 3? That's it?
Multiply it by square roots.
Square roots of 3.
Multiply it by square root. Multiply 5.5 by square roots of 3.
Alright. Multiply the length of that short leg by 5 square roots of 3. So if proper fraction, it would be 11 halves square roots of 3, or 5.5 square roots of 3. Now if we investigate this triangle even closer, we'll see that the apothem, which is what they're asking for, is the side that's opposite this 60-degree angle. And so my apothem's length would be 11 square roots of 3 divided by 2. That's the answer I prefer. However, 5.5 square roots of 3 is okay as well. So they're just getting us closer and closer and closer to solving for the area. Now let's go to the next page. On the next page is where we get to the meat. On the next page is they tell us to find the area of these regular polygons, and they give us an array of different information. Sometimes they give us the radius, sometimes they give us the side length, sometimes they give us the apothem, and we just got to take whatever we're given and solve for the area. On number 14, what are we given? We're given the radius. What else are we given? It's very, very obvious. What? Yeah, we're given it's a hexagon, right? So we're given n, the number of sides, is not 3, is 6. And we're given that the radius is 8 units. They chose to stop putting units, I guess. So we're just going to put a U for them. So this is a hexagon, n is equal to 6, and we are given its radius. Now our end goal is to find the area. To find the area of these regular polygons, we're going to use that formula, 1/2 times apothem times the perimeter of the polygon. So we need the apothem's length, and we also need the length of one of its sides. Now, sometimes when they give you diagrams, they'll make it big enough that you can just start drawing inside that diagram. You can start drawing in the radii, you can start drawing in the apothem lengths, and you're all good to go. However, these are pretty small. So I find it most common with my students in the past that they will just they'll draw their isosceles triangle that's created by 2 consecutive radii and the side length, they'll find out what this central angle is, draw in their apothem, and then they'll draw the right triangle that they need to solve that's being created by the apothem, 1/2 the side length and the radius. They'll draw that really big so they can write the angle measurements inside and they can do all the trig or whatever they need to do. So, to each your own, but I find it most convenient just to do this. Just redraw your triangles with the appropriate segments a little bit bigger so you can write inside of them. So, for this, what is our central angle measurement? That's created by 2 consecutive radii. And Kara, how'd you find that? And you got 60 degrees. Awesome. So that whole central angle is 60 degrees. But then, Ian, what do I got to do next? But why?
Because the apothem bisects the triangle.
Good. Well, bisects this vertex angle in that side of the regular polygon. And so yeah, we just introduced that apothem and we know what it does, the 2 things that it does. It bisects that vertex angle and also bisects this opposite side. So this is where my students would be like, okay, I'm done with that diagram. I'm going to draw my own little right triangle that's created by apothem, 1/2 the side, and the radius. And they can always draw in the measure of this angle that's being created by the apothem and the radius. In this case, what is the measure of that angle?
30 degrees.
30 degrees. And then we can write what we're given. We're given the radius is 8. Do we really need the radius length to solve for the area? Like, is it imperative to have the measurement of the radius of a regular polygon to know its area? But is it imperative? Must I have it? Like, what if I say, hey, the apothem is 10, the perimeter is 60. Do you need the radius?
No.
Okay, cool. So, if I give you the apothem, or if I give you the side length, don't waste test time finding your radius. You don't need it. Okay? But this is a problem that will require the most work. Because you're only given the radius, which you really don't need, and so you have to use this radius to find 1/2 the side length, then you're going to double it to find the whole side length, and then you're going to multiply that by however many sides there are to get the perimeter, and then you're going to have to solve for the apothem. So when I give you the radius, that means this is going to be quite a trek to get to our final answer. Okay, this is one of our 30, 60, 90 special rights. So again, 30, 60, 90, L square roots of 3, 2L. Again, I'd say this all the time, but what I write on the board is what I expect from you. I practice what I preach. So I write on your quizzes must show work, like I do it. I've been doing this for a while, and I don't need to do this. Like I can tell you right now, it's 4 and 4 square roots of 3. I don't have to go through this, but I expect this from you, so I throw it on the board. This is the minimum requirement of work that's got to be on your quizzes and tests. So they give us 8 units. That's the hypotenuse. I'm going to divide that by 2 to get the length of my short leg. 4. I'm going to take that length of the short leg, multiply it by the square root of 3 to get the length of the long leg. So I've got that 1/2 of my side is 4. So what is one whole side length of this regular hexagon? 8. This only happens in hexagons. Please, 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 please listen. This only happens in hexagons, where the radius is congruent to a side length. This only happens in a regular hexagon, because when you draw in these 2 consecutive radii, we found out that that angle measurement is 60 degrees. Well, because this is an isosceles triangle, its base angles are congruent. So the leftover 120 degrees is being split up evenly between these. So this is an equilateral triangle. It's also equiangular. So it only happens in hexagons where the radius is the side length.